So I've adjusted the schedule slightly for today. I know in the original agenda, years actually, I had a session around sort of maintenance, cluster maintenance, and business continuity and disaster recovery. But obviously, I think these concepts are much better to sort of demonstrate in real time, and it wouldn't be a true demonstration on my local environment. So I'm going to shift that as a bit of an exercise that we do as part of the sort of proof of concept walkthrough, because it's going to be much easier to sort of show you what it's really going to be like in an AWS environment as opposed to a development cluster that's running on my local machine. So what I wanted just to talk about today was, we're basically, giving you guys an introduction now to Kubernetes, how you deploy workloads today, how you operate them, how you monitor them. And the last sort of topic to close all this off really is looking about, sort of scalability and capacity. Now, in your cloud environments by design, they're sort of elastic. The idea is that they respond to demand automatically, which encourages, an efficient use of your cloud resources. And I think sometimes I feel like one of the common misconceptions with cloud migrations can be that you're automatically going to sort of save lots of money, and a lot of the time that isn't actually the case. What you're actually doing is giving the organization a lot more sort of purely from an infrastructure point, an operational point of view, a lot more sort of agility, a lot more flexibility about how and when you release and things like that. Renting and again, one of the key sort of activities that sort of needs to happen on day one is to make sure you understand how your cloud costs are going to be affected and how you manage them before you start firing lots of traffic at it, because it can the bills can ramp up quickly if you're not using these cloud services efficiently. So let's say, why do we want to do this? Any organization worth its salt, they're going to want to establish and maintain the cloud's capacity and availability for its end users. But they do want to do that at sort of at a justifiable cost. It's one thing saying that, okay, well, we're no longer going to spend 50,000 pound or GBP on a new server for our on-premise data center. But then if you end up spending 150,000 over the course of 12 months in the cloud environment for the same capacity, then sometimes the actual numbers don't add up, and you've got to be careful that you've got somebody in place to sort of do that sort of technical governance and capacity management exercises before you sort of really kick off your cloud migrations. And the main reason for this is, like I say, the three things that you primarily pay for. If you don't use any of their sort of value-added services with cloud providers, you're going to be paying for your network, your storage, and your compute. So, with a network, what we're really talking about here, the primary costs are sort of egress traffic from the edge of your cloud over the public internet, and sometimes people just think that traffic coming in is the only thing that would affect that cost. But anything, any of your servers that use their sort of proprietary update managements, whether it's sort of Linux, apt or Yum or anything like that, anything that generates traffic outbound to the internet is going to incur a cost. And things like software updates on Linux systems can catch people out and generate lots of additional egress costs, and then get hefty bills. I had a customer once that basically wasn't very good at keeping their machine images up to date. Over the course of time, every time, and they use spot instances, so they recycled lots of these instances over the course of the day. They would spin up, be used, disappear, spin up again, and over time, their cloud bill started to rise excessively, because every time these machine images or these EC2 instances were being provisioned, they had to download huge swathes of software updates before they actually processed or did their job. And if you haven't got the correct sort of monitoring capabilities in place that are looking at these things, it can certainly catch you out in your sort of early days in your sort of cloud adoption. The other big sort of, I see sometimes unforeseen costs can relate to storage. Storage is cheap, but the more you put in there, the more expensive it gets. And different organizations have different requirements around their sort of data retention. You can imagine in banks and places that work in or work within sort of quite secure industries. They need to retain their data for potentially years, and you've got to. It's not, you don't store that in a database where you're paying, a premium of cost for provisioned database storage. You need processes in place to take that data and move it to somewhere a bit cheaper within the cloud. For example, if you're not too familiar with AWS, you could take your database data from, say, Postgres and move it to S3 after maybe 30 days if it's no longer really required for sort of day-to-day running of your applications. And then you could, again, maybe after 90 days, you move it to AWS Glacier, which is on sort of long-term storage, but your sort of cost per gigabyte, if you like, is really low. So it's really important you obviously have a data retention strategy as well. And finally, you've got your sort of compute resources. So again, when we say compute resources, we're talking about EC2 instances that are provisioned. We're talking about the cumulative execution time of a serverless function, because obviously we haven't got any actual or any requirement to manage the underlying infrastructure yourself. And even with things like with Fargate, I mean, it's not obvious how you manage those costs efficiently, because really there's a trade-off where Fargate and sort of EC2 within a Kubernetes setting become Fargate becomes more cost efficient, but it's all around the commitment of resources that you're requiring from AWS. If you're not making big commitments, then typically you get a less competitive price. So I'm going to go through the list a little bit different. So purchase options. So purchase options relate, like I say, to sort of your standard EC2 instances. On-demand prices are set. You can go and view them for every different type of EC2 instance type they have, for every size they have as well. So you've always got an idea of what the on-demand price of your reference architecture would cost you from an EC2 point of view. However, generally speaking, if you've got a predictable workload and a predictable capacity, it's almost always beneficial to sort of leverage the reserved instances, which is basically it's you committing to usage, a certain amount of usage for either 1 to 3 years and paying for that up front. However, you can sort of amortize those sort of costs, if you like, over the year, which sort of helps with sort of cash flow, cost planning, and etc. And you can make some quite significant savings over the on-demand prices. So depending on the instance type and class and type and size, you can save up to 40%. And the thing to consider in those sorts of scenarios is, if it's not always the right move, and I'll get into that in a little bit more detail, but it's only worth doing if your servers are under load for more than 40% of the time, if that's effective. This is not a Kubernetes thing now. If you had an EC2 instance that's only being used 30% of the day and you've got no load outside of that window, then it's actually cheaper just to shut the instance off for the period you're not using it. So you still need to have a strategy. You still need to understand the workloads you're running and how to manage them effectively from a cost point of view. The other alternative you've got is obviously AWS is absolutely massive. The data centers are massive. There's people not using their machines at certain times of the day, or AWS not using some of their capacity at certain times of the day. So they have a marketplace where you can basically bid for spare capacity of a particular instance type or class, and you can get it exceptionally cheap compared to on-demand prices. So it can be up to 90% price difference, really. And funny enough, when I was doing the POC, I was using spot. They're called spot instances, basically. When I was just sort of iterating on the POC in my own private cloud, I didn't want to pay on-demand prices. I couldn't commit to for this sort of work to 1 to 3 years up front. So I configured my Kubernetes cluster to use spot instances, and I was paying a fraction of the price that I would pay if for that sort of development work. So it was costing me pennies really every day just to run the cluster for 3 or 4 hours while I was doing some work and doing some testing. However, again, some caveats here. Because they're spot instances, they could be taken back. What that means that if the EC2 instance might be running on a process, it might be running containers, it might have Docker installed in it, might not. It could be interrupted. So there's about it's not too bad. I think it's about they guarantee about a 90% SLA or something like that of uptime. So there is a very small chance that your workload gets interrupted, which means architecturally speaking, whatever workload you're running on those machines needs to be sort of fault tolerant. So if you just go back to the sort of example I said about the costs for the spot instances at a previous customer I was working with, what they were using it for was to pick up messages off the queue, process those messages to convert some videos. So back in that case, the spot instances at an architectural level made a lot of sense because it was cheap. There was no real SLA attached to processing those videos. So they just had a queue within AWS using the SQS queuing service, and they would just pick up messages off the queue and process those videos all day, every day. So in that case, spot instances was absolutely the right way to go down there. Yeah, you could, and excuse me. So again, let's moving on to storage. When we're talking about data retention strategies, again, what do we mean? So what I think it means is we have to perform regular housekeeping. So if you think of things like if you've got backup tools in place that are taking backups of your EBS volumes that are attached to your EC2, so your disk volumes, or you're using RDS and you've got automatic backups and it's taking snapshots of your database on a regular interval. By default, all those things, well, even Docker images, Docker images is another good one. You build and publish lots of Docker images frequently to ECR. By default, all these things, all these storage costs will slowly accumulate over time. So it's always very good to put these processes in place and these policies in place to remove things that are no longer required. And it's obviously very specific to the type of thing that you're doing and the type of data that you're storing and what your requirements are. But I would always recommend that at least a first pass at these things to ensure that you're from day one, you're not going to get caught out by rising costs. And if you don't know what they are, then my suggestion would be to create budgets within your account, alerts when the resource usage on certain services goes over a certain threshold. So at least then you can maybe go back afterwards after the fact and say, okay, well, we need to do a piece of work to housekeep these items because we're not using them, or we thought we were going to use them and no longer. It's not a one job you do and then it's done. It's a constant part of running a cloud, and whether you're doing hosted PaaS or you're building your own platform, that you will have to still manage your data within that environment. And one of the other things that's obviously very popular to do for things like your static assets, websites, website static assets, is actually to cache the data at the edge of the network. So you're not actually paying for all those egress costs. So you can imagine, you've got a static or single page application. You might be tempted to deploy it as a Docker container within your cluster. However, what that does mean is that all the traffic would be coming from your cluster, so consuming some of your cluster resources, and you'd also be paying egress costs on any of that traffic. So anytime somebody went to your web page and the assets weren't cached, you'd be paying for that for them to pull those assets down again. So using services like Cloudflare, where effectively you don't pay for the egress, is obviously a really good idea to do in sort of productive systems. I mean, in dev and test, you might not do it. You might be happy just to run it within the container within your Kubernetes cluster. And actually, a colleague, a friend of mine who I did some work with before, he pointed something out this week, which was good timing, about somebody who literally writes about managing your cloud costs, and he got stung with an issue with Cloudflare when he was trying to cache. I think Cloudflare had a limit of 15. I think it was 15 megabytes. No, 15. Yeah, 50. Yeah, he had a limit of 15 megabytes on Cloudflare for caching, and he was caching something that grew just above the threshold, just a fraction above the 15 megabytes, and all of a sudden, Cloudflare stopped caching the item for him, and he was serving it from his own servers within AWS. And I'll show you at the end, because I think it's a good sort of case study in why these things are important. But he ended up incurring something like 11,000 Australian dollars in his AWS account for that month, until he was able to request the 15 megabyte limit to be raised by AWS support services through their quota service. So yeah, you can find plenty of stories where this goes wrong, and it can really sting businesses if they're not prepared for it. And then finally, the other sort of mechanism we can use to sort of manage capacity is sort of software defined policies. So what this really means, or translates to, is what sort of strategy do we want to use in terms of managing our capacity? Do we want to scale up, or do we want to scale out? And they both achieve the same thing in a roundabout way, but they have different mechanisms and how they go about it. And they might have different impact on your sort of end users. So sort of scaling up is just making a machine bigger. Scaling out is creating more of the same thing that you've already got, and increasing your capacity that way. So again, what I'm trying to do here is just categorize what this means at a sort of infrastructure level and a platform level, because we are sort of talking about different things when we think about scaling up in those sort of contexts. So when I talk about scaling up at the infrastructure level, it means changing the size of the EC2 instance, for example, or the RDS instance. At the platform level, it means sort of increasing the resources that you've allocated to a specific pod or container. So scaling up increases throughput, but it may create service disruption, which is important, really. So if you think about a case where you're running an RDS database, and you decide, well, looking at the performance metrics, and you can see that the traffic is now increasing to a point where you need to scale up your database, okay? Because traditional relational databases don't really scale out that well. You can't just scale it up without any interruption. You would have to update your sort of infrastructure code to say use DBM5 2XL, for example, and then you would have to basically stop your database in order to flip over. Now, in a DR environment, then you would have a way to do that without any service disruption, but obviously in a non-HA environment, then potentially you would cause some impact to your end users. So again, it comes down to what your actual environment looks like based on the sorts of workloads that you're spinning up. And then scaling out is sort of the equivalent at the infrastructure level, is increasing the number of EC2 instances. So this would be, so for those who are not familiar with EC2, you can go and provision a single instance, that's fine. If you want to spin up many instances and sort of operate them as a group, then you use an auto-scaling group. And you basically create a template that says, well, this is what my server looks like. Attach it to the auto-scaling group, and set a minimum and maximum level for the pool, and AWS will manage that level and maintain a fleet of EC2 instances within that pool. And you can do some additional customization around that. For example, you can decide what metric you want to sort of scale up or scale down on, or if you want to do it on a schedule. If you've got predictable workloads, you could maybe increase the number of EC2 instances for a short period of time to get you to your peak, and then you can spin them down afterwards. At a platform level, it means increasing the number of replicas. So we've already introduced you guys to sort of the concept of the deployment, and deployment manages a pod. And there are many instances of a pod, and the fleet of those instances are replicas effectively. So what scaling effectively it does for us is increases our sort of fault tolerance, because we're actually spreading the work over more individual nodes, if you like. So if you think about this scenario where if you run everything on one machine, if you lost that machine, then you wouldn't have any availability in your system. If you run the same workload over 10 machines, then if you lose one machine, then you're very likely, and the blast radius and the impact is going to be somewhat mitigated. And the nice thing about scaling out, generally speaking, is that these tasks can sort of happen in the background. They don't need to be, they can be automated, and your end users wouldn't necessarily know they're happening. So one of the things to just bear in mind that, sometimes the difference with scaling and scale out is like scale out, if you think about it, can be a little bit more manageable in terms of like the unit increase in capacity can be a lot more granular than maybe scaling up. So, once you start to get into the bigger machine classes where a scale up would add, you'd go from 32 vCPUs to 64 VPCs, and maybe you go from 512 gig of RAM to a terabyte of RAM. If you only need a little bit of capacity, then that becomes quite an expensive task. It's not saying it's not the right decision. It depends on your sort of increments of your scaling needs or your capacity needs. But you can see how that can become quite an expensive exercise for people. And if that additional capacity isn't covered by a purchase option, like a reservation or something like that, then you'll be paying on-demand price for that additional, what was the example there? The additional sort of 64 VPC CPUs and half a terabyte of RAM. So again, just be mindful of these things are always happening in your cloud, whether you're using a hosted version or you're building your own, and they need to be sort of accounted for and managed. Otherwise, you can find your cloud costs getting out of control. So the goal really is to sort of how do we cost optimize all this? How do we put the things in place in order to sort of try and mitigate these and prevent these sort of unwanted costs from occurring? So we've already established that the main majority of cloud costs are going to come from network storage and compute. A lot of the time, the initial cost savings will come from the compute resources, because if you're spinning up on-demand prices to begin with, then over time it's really going to get expensive, and the first thing you'll iterate around is moving to using pulling all the different levers to sort of control those costs to a manageable, stable, predictable level. Data tends to grow linearly, if you like. So the costs there are quite predictable. They don't tend to, unless you're aware of a new service coming online that's going to generate a lot of new data. You can sort of predict those costs, but as part of a whole, if you like, of your AWS build, most of the cost is going to come from the compute level, and then probably the network level from egress costs. When we layer over sort of Kubernetes over the top of this, what it really means is the number of is the resources that you've allocated to a pod, and how many pod hours. So the number, if you added up if all you had 5 deployments running 24 hours a day. Let's make easier maths for that actually. All right, you had a single deployment with 2 replicas running 24 hours a day. That would be 48 sort of pod hours, if you like. If those pod hours, if the resource attached to that pod was sort of one gigabyte and 1 CPU, then obviously you can predict how much resource roughly you're going to use in terms of instance hours, and what EC2 instances you need to accommodate that workload. So they are sort of intrinsically linked, if you like. And there's a few things that we can actually do, like a few activities that when we stand this initial environment up in order to sort of start to get these costs under control and make sure we're doing the right thing. So the first one is obviously auto scaling. So we've sort of touched up on this in parts of the session. And what it really means is sort of we're going to optimize the instance hours, so the amount of time that our instances are running, by aligning the number of sort of, let's call them nodes or EC2 instances in the cluster to the demand. So if we only need shall we say, let's just take that example again. So if we only need sort of two CPUs and 2 gig of memory for this one deployment over the course of a 24-hour period, then you wouldn't go provisioning a 64 vCPU EC2 instance. You'd probably take the smallest possible version of that. Now, that would probably be something like a four VPC, 4 vCPUs, and maybe 8 gig of RAM, because that's the smallest sort of machine you'll be able to get that could reliably fix that, run that workload with a reasonable amount of network bandwidth, shall we say. The second exercise is something we call right sizing. So it's basically fitting the pod resources efficiently into your fleet of nodes. And we do this by setting the appropriate sort of CPU and memory limits on the pods. So until this point, all we've done is just deploy the pods, or created a deployment that deploys some pods, and there's no resources attached or allocated to that. So I'll go into this in a little bit more detail in a couple of slides, but effectively it's going to consume as much resources as it needs to do the job. There are no bounds on what it can consume from the underlying operating system. The next thing we can do, obviously, is called downscaling. So what we're doing then is, I sort of alluded to this before, if you've got workloads or deployments perhaps that are literally under zero traffic for portions of the day or during the night, then you could just remove them or scale them down to zero so they're not running. And this might allow your auto scaling setup to rein the number of EC2 instances you're running in, saving you some money, which is obviously nice. And these things have got to tie up together with things like reservations as well. And as you can see, the last thing here we can do is sort of optimizing the instance price by replacing sort of the on-demand instances with spot instances. But this comes at a cost. Like I said, if you can run your Kubernetes container or your pods on spot instances, but if it gets interrupted, then those jobs are going to be interrupted, and they will move on to other nodes, so that those nodes will be replaced, but it obviously just has to factor. So this is maybe a good thing for like background jobs and things like that. They can be interrupted and they can start again. And if we step out a bit, then what we should be looking for really when we come to cost optimization is something that looks like this. So, over on the left-hand side, we've spun up our environment. It's running, it's in production. We've got customers using the system. So the costs are high. Daily costs are high, and over time we got the first sort of pass we do dramatically reduces and optimizes those costs. I mean, this is just an example time period, but we systematically go through those 4 activities to bring the cloud costs under control, because it's one of those things where if you don't know how much it's going to cost, I mean, you might be able to do some of these up front, but it sometimes depends on the sort of the type of workload you're running. And this is even maybe an exercise that needs to be done every time you bring a new application or a new sort of customer on board. I understand how it's going to impact the cloud costs, and have you done these exercises in order to sort of mitigate and make sure you're running your cloud environment as efficiently as possible. So I'm going to just take a little bit of time talking about what this actually means in reality in terms of the workloads that are running in your cluster. So we've talked a lot about sort of auto scaling in general, having that elastic capacity that spins up or increases and decreases with your load. But how do we sort of achieve this within sort of Kubernetes effectively? So by default, when we've deployed or created deployments in the cluster, we've set a fixed number of replicas, all right, and a lot of those examples. But we do have the freedom to tell the Kubernetes control plane to increase the number of replicas for any given deployment, all right, just by using this kube control scale command here that you can see. So you can set it to 0, you can set it to 1,000 if you want, all right, and it'll update the deployment in place, and it will start to provision or terminate the new pods or the existing pods. This is all well and good, but obviously if you've got a potentially volatile workload that sort of goes through peaks and troughs of traffic throughout the day, then you would need somebody there to basically manage this. You either make the decision that you're happy to set your capacity to accommodate this and don't touch it, but obviously then through large periods of the day, you might be spending money on compute resources that you're never really using. So this is part of the whole point, is that you're controlling the efficiency and the density of your workloads within these instances. But it's not really practical for somebody to sit there monitoring the traffic up and down all day. So what we can do is we can create something called a horizontal pod autoscaling, which is basically something that monitors the metrics on your behalf. So it basically does the job that you would be doing of monitoring dashboards, etc., and running commands. And it would automatically scale up and down the replicas as it deems necessary. It triggers on standard CPU metrics by default. So the CPU and memory of that particular pod. So if you remember, because of the way Docker works, you've got that kernel isolation. You can get very accurate statistics about how much CPU and memory are being used by a given pod. But you can also plug in custom metrics. So you are able to plug in metrics from Prometheus. So if you had a custom, your service or your pod had a metric for the number of currently sort of active users or logged on users, you might decide that that's a better metric to scale up and down on, because it's a bit more predictable. And you could plug that in, and if your user load went up, then so would the number of replicas of that particular pod servicing that load. So it can get quite cool about the things you can do on there. One of the key requirements, though, for this to work is obviously you need a metric server to be deployed into the cluster. Well, we sort of did that yesterday. If you remember, we had Prometheus running. Prometheus is able to scrape the metrics from the metric server, which gives us all the metrics around the nodes and the containers themselves. So not the application metrics as such, but every container that's running within a pod publishes its metrics using a tool called CADvisor. And the metric server basically scrapes and aggregates those and publish it and makes it available to Prometheus. So this is why we were able to have all that information sort of out of the box, if you like, without any additional configuration. So this is what the sort of manifest looks like for a horizontal pod autoscaler. Again, very, very similar to what we've seen. We specify the metadata. That's generally speaking, you tie it to the deployment, so they're all related via the label mechanism. You specify the target, and you, in this case, we're going to target the HTTP bin deployment. You can specify your maximum and minimum bound. So again, if you want to sort of limit how many of these you're actually running, so because somebody can't scale up to 1,000 or can't scale away to 1,000, then you can do that through min replicas and max replicas. And then you just list the metrics that effectively that you want to scale on. So in this case, I've created two scaling metrics. So I'm gonna try and achieve a target average utilization of 80% on the memory and 80% on the CPU. And what this really means in reality is, if the metric server is scraping the pods on that deployment and it averages the CPU across them to below 80%, then it will scale down the cluster. And if it's above 80%, it will scale up the cluster. So it's quite simple how it works. Obviously, there's some statistics and some aggregations in there that need to sort of average out in order for this to function. And it would be no different to if you use the custom metric. So a number of users, it would be an absolute value that you would give and say, well, above 1,000 users, I want to provision a new pod. I'm not going to show you any demos for this today, just because it doesn't really make any sense to do this on my local machine, and there's a very good chance that if I try and create load on my local machine, I'm going to completely destroy and probably bring down my machine, and as well as the Kubernetes cluster that I've got running. However, what I have done is I have set this up in the proof of concept, and I have written a few load scripts to sort of generate realistic load. So what I did is I wrote a little controller just to calculate prime numbers using big O notation, just a few different ones, different complexity ones. So I could sort of generate CPU load on the container and trigger the auto scaling based on the CPU metric. So that would be a good thing to go through when we do the POC. The second sort of part of the auto scaling is the cluster auto scaler. So previously we're just talking about scaling the pods. The second sort of component, if you like, within your cluster is the cluster autoscaler, which manages scaling out your underlying compute resources. So your EC2 instances effectively. We're not actually using AWS to do that because very specifically, AWS would look at things like CPU and memory because that's what it's got visibility of. But that doesn't really make a lot of sense when you're running Kubernetes, and specifically the cluster autoscaler doesn't look at memory as a metric about when to add a new EC2 instance or take away a new EC2 instance. It looks at the number of unscheduled pods. So if you remember, the control loop is constantly looking at, or the controller manager is constantly looking at the workloads that are being submitted to the API server, and those pods are getting sort of spread out across your cluster, which is great. At some point in time, you will run out of resources because all of those pods have got resource limits attached to them, and they'll consume the available resources that you've got on node, and you'll get to a point where effectively you might scale up deployment, sort of say from 2 replicas to 5 replicas. It might provision 2 of them, but then the last one is unschedulable because there's nowhere left within the pool to allocate that pod to. That's when the autoscaler would detect and trigger an underlying call to the cloud provider to provision a new EC2 instance, basically. And when that new EC2 instance has spun up and joined the cluster, the pool of resources, then we can schedule the pod and it can complete the request. But again, I would say a lot of these buts, but it's always good to be aware of. As much as we think, or we used to think, provisioning EC2 instances is fast, in this context, it's not. It's actually very slow. If you get a spike in your traffic within your cluster, you want to be able to respond by scaling out your capacity as quickly as possible, almost instantaneously. I mean, if it was very less than 60 seconds or something like that, enough for, but that doesn't happen in this scenario, and this is why. So this is the potential lag time. So in this hypothetical scenario where we've got 1 unscheduled pod and we've asked it to scale out from 2 to 5, 2 of them have spun up and 1 is still unschedulable. It could take potentially in a small cluster, what's that, 6.5 minutes for your pod to become accessible and for your application to become, to increase its capacity. And the reason for this is you can clearly see that the majority of that time is actually spent provisioning. So it doesn't matter how you can't increase the boot speed within EC2. If you're using their managed machine images or their stock machine images, they'll be as quick as they are. They're not going to boot up any quicker from anything that we can do. So that is a cost that we're going to have to absorb somehow in this process. The other additional costs, like I said, a bit worst case scenario, this is you've got the metric server, which is running in your cluster. The metric server every 10 seconds is basically collecting metrics from the Docker containers, the CPU usage, memory usage. Every 60 seconds, it will aggregate all that data together and basically make it available to the Kubernetes API. And at this point, because it's in the Kubernetes API, then the horizontal pod autoscaler is able to see those metrics and then make a scaling decision based on those metrics. And the evaluation time within the horizontal pod autoscaler is about, by default, is about 30 seconds or something like that, or maybe 20 seconds. But if you add all those sort of worst case scenarios up, then effectively the point in which the horizontal pod autoscaler would make a scaling decision could be up to 1 minute 30 after you've given a scale out or you've had an increase in your traffic. Then you've got to wait for the cluster autoscaler, which is a separate pod that's running in the kube system namespace, to also complete its control loop. And its control loop will basically every 30 seconds to begin with, or by default, obviously we'll evaluate all the nodes, evaluate all the unscheduled pods, and then make a decision as to whether it needs a new node. And that's all open source. You can actually see exactly what it's doing in terms of its evaluation logic, and determines whether you need to scale up or scale down effectively based on the number of unscheduled pods and the overall resource utilization of the cluster. It's only at that point that you're actually going to make the call to start a new EC2 instance. and then you've got to wait at best 4 minutes on a small instance. If these are large instances, they might take a little bit longer. And then once that node is joined the cluster, we've still got to pull, if this is a new instance, it isn't going to have your Docker image cached on it. So, we try and make our Docker images as small as possible for partly for this reason, because that's the intention. But sometimes you can get quite large images, 500 meg, a gig, that you've got to pull down before you can even start a container on that particular instance. And there is benefit in more advanced sort of setups to actually, attaching maybe an EBS volume to your nodes that already have the Docker, a lot of the base Docker images that you use on it. So you haven't got it, you can save yourself 30 seconds on the right hand side then, because your Docker images are already there in effect. So how do we combat this, I guess, is probably the question I'm asking. What can we do? Well, the obvious thing we can do is we can make sure that at any given time we've got spare capacity in our cluster. We can have an extra EC2 instance just sat there doing nothing. We're paying for it, it's idle, but we've got extra capacity. And anytime we need to dip into that, anytime we need to dip into that capacity, we can. And soon as something lands on that machine, we can spin up another one of those, if you like, in advance. However, EC2 autoscaling doesn't support that model really. It has no awareness of it sort of provisioning in advance. That would have to be a manual task for somebody to basically say, oh, okay, we need to change the desired number of EC2 instances in this autoscaling group from 5 to 6 as soon as we see that at least one thing is scheduled on our spare node, because otherwise all will happen is that node will fill up and then you won't have any spare capacity. So, again, you're trying to think about these things in real terms. But what you can do is you can do something a little bit interesting, is that pods, and we're going to get into a little bit more pod semantics here. Kubernetes supports different sort of priorities, if you like, of pods. So what you could do is you deploy a pod, if you like, to that spare machine to hold it in place. So, however, it would be a pod with a very low priority, and it would consume more or less all the resources on that machine. So it sort of sits there, doesn't do anything. It makes sure that you've got that EC2 instance there in case you need it. However, if it is needed, because we've got an unschedulable pod, because it's been set with a very low priority, that pod gets evicted and automatically and becomes unschedulable again, if you like. But it's replaced with your actual pod that you want to run. And then what would happen in that scenario is then you're back with having an unschedulable pod. The cluster autoscaler would spin up a new EC2 instance, and it would then schedule the low priority pod back onto that and keep it there and hold it. So you can do this automatically. It's not a huge amount of effort to set up, but what it does give you then is a much quicker turnaround whenever you want to scale up. You've always got that sort of spare capacity. And again, it depends on the traffic and the shape of the traffic that's coming into your cluster. It's very difficult to answer these questions without knowing exactly what that looks like. And it's different from everyone, whether you need to set these things up. So moving on a little bit now, the sort of second exercise that we need to go through is the sort of right sizing exercise. And if you remember what I said, this is about making sure that you've got you haven't over provisioned your EC2 instances for the type of things you're deploying on them, and you've also sized your pods as well to a reasonable size, because both of these things, if you get them wrong, can have sort of impact on the efficiency of your cloud. And before we start, it's obviously really important to understand that not all of the sort of CPU and memory is available to your cluster. For obvious reasons, you've got an operating system running on there, you've got some system services that are going to be running on there, you're going to be running some of the control plane elements on there. So if you provision a sort of 2 CPU for let's call it 8 GB node, you're only going to get probably something like 1.7 worth of CPU and maybe 6.7 gig of RAM. So just something to bear in mind when you actually go through the exercises, you need to allow some overhead when you're sizing the instances based on these things. And there's also a little bit of room reserved from a Kubernetes point of view, which is called the eviction threshold. And that's like a hard line on a node. So if at any time a pod sort of dips into that eviction threshold, if you set it to be a hard eviction, it will evict that pod and try and put it somewhere that's better suited to it, where there's some more capacity. Because what Kubernetes, what the control plane is constantly trying to do is avoid, keep your systems running. So it doesn't really want to allow your pods to get close to consuming all the RAM or consuming all the memory. It wants to take it close, but it doesn't want to take it that close. If it makes sense, it just leaves enough that the system, so the system can still function under heavy load. And it makes the decision, like you say, it'll move a pod sideways somewhere else that's better suited for it if it gets above the sort of eviction threshold. And there's a little diagram here on the right, which sort of shows where the sort of sweet spot is in terms of efficiency across the different clouds, in terms of the memory and the CPU available to the pods and how many pods. So obviously the size of the instance completely determines the number of pods you can run on it. And you can see here it starts to sort of flatten out around the sort of 64 gig mark. But again, that might be too much for a dev environment. You wouldn't want to provision one 64 gig server for your dev environment. You'd probably want to maybe provision four 16s instead, or something like that. So you've got a bit of fault tolerance, you've got a bit of high availability in there. But in your production environments, it's very likely that you'll be using a lot more resources to accommodate the load. And you, like I said, you'll find the sweet spot. And it is about testing. You still can't build these systems without doing a degree of testing. How this translates to sort of hosted providers, I can only make some assumptions, really. I would think that if they can't do this as efficiently as you can, because you understand your workloads better than they do, they will do it in a very generic way, which probably isn't the most optimized way. And probably partially explains why the general costs of hosted platforms are bigger, because they need to accommodate for those sorts of little inefficiencies, because they need to apply the same rules to pretty much everyone. So this is something we've not really had a chance to talk about yet. But what we can do is we can assign, not only can we sort of pick a good instance size, if we're doing a CPU based loads, we can pick a CPU class instance. If we're doing disk-based loads, we can pick CPU instance types that are with good network throughput, and even ones that are for memory. Or you can just pick a general purpose one. A lot of the time, your general purpose ones tend to be cheaper than your sort of specialized ones because of the sort of configuration of them. But again, that's your first port of call. Pick the right instance class and size for your environment. The second thing we can do then is we can actually instruct the control plane as to how much resource that we want to actually give to our pods. And this is through the resources attribute. So it's for you apply it to any container. So in this example here, we've got actually two containers. We've got a Redis container and a BusyBox container. And they've both got the resource attribute on the sort of specification. And there's two types of settings effectively that we can control. We can control the limit. So, above, basically in simple terms, above which Kubernetes will either throttle the CPU or kill. So basically kill the pod with an killed error code, which basically means it's consumed too much memory. And we've got a requests attribute, which is sort of the minimum, if you like, or say under what you would expect the average load to be. And at this point, below which it wouldn't matter. That's your sort of baseline, if you like. So from that, you can sort of say you can determine really how much capacity or extra capacity here have we done. So what we got here in the example. So if you look at the Redis example for here, we're actually expecting most of the time the pod to be using about 300 meg of memory, and we want to set a hard limit to sort of 600 meg. So we're actually over provisioning, if you like, that pod by 300 meg. And if you do that extra 300 meg across 5, 10, 20 different workloads, that can obviously add up and make your cluster quite inefficient. Conversely, if you look at the BusyBox, well, the BusyBox isn't really doing anything. It's a sort of sidecar container that's probably, you know, not doing anything particularly important. So it's been given a lot less memory. But you can see here, if you just follow the sort of the numbers here about how Kubernetes basically allocates all this into the cluster. You can work out the effective, you know, pod request, which is the sort of the sum of the requests from all the containers within the pod in terms of the memory and the millicores. So we don't work in CPUs here. We talk in like CPU shares, which is sort of a much more granular slice of the CPU, so it can be dished out effectively at the kernel level. So you can work down all. I think you can go down as far as, I think the lowest you can do is probably 1, if you like, or yeah, one sort of millicore effectively. So you've got really fine-grained control over how you want to over how much memory and CPU you want to give to your pods. So you can see there in point 2, Kubernetes assigns 124 shares per core. So you can sort of work out then how many CPU shares that this particular pod needs on the CPU. And again, what I've just said, you know, point 3, the pod will be killed if it tries to allocate more than sort of 600 megabytes, and that if you look at the container status, it will be in an error. If you look at the events attached to that container, it will tell you it's been killed because it's out of memory. So you've always got visibility of what's going on. From a CPU point of view, what will just be happened is that it's throttled, so its capacity is limited. So if it does require more CPU than that to do its job, it's not going to get access to it. The underlying kernel is going to sort of prevent that. And similarly here, points sort of 5 and 6 work exactly the same way. With the limits, the pod will be killed if it goes above 200 meg, and it's throttled if it uses more than 30 milliseconds of computing time within 100. That sort of slice effectively. Oops, sorry. So one of the things you wouldn't want to do in that case is allow people to deploy applications into your cluster without any resource limits set, because you can see how this would quickly get out of control, and you wouldn't be having any visibility into well, effectively all your pod resources would interact with each other, and certain one deployment would starve another deployment of resources, and it would have unexpected behavior. So everything to this point that I've shown you, and any deployments that I've done within my local cluster, I've basically not set any pod limits whatsoever. So it can consume as much resources as it wants from the node that it's deployed to. And this is what we call a best effort class, so quality of service. This is something that's maintained again by Kubernetes internally, that you don't necessarily have to deal with too much, but it's good to be aware of the semantics behind it. And if you use kubectl to describe the container or the pod or the deployment, you'll see it'll have an attribute next to it with the QoS, the quality of service class that's been assigned to that particular pod based on the pod limits that you've specified. So scenario 1, everything we've done today, no pod limits, it gets a best effort class. It can consume. So if I run a little Java program that every second allocated, 512 kilobytes of memory, over time that would consume everything on my machine and probably bring down the node in its entirety, which is not what we want. But it's fine for sort of development environments, things like that. It isn't a problem. The second scenario, which is the scenario in the previous slide, where we've separated out, well, we've allocated a limit, and we've allocated requests that are below that limit. This is called a burstable class. So in terms of allocations onto a node, the control plane would use the limit because that's the maximum it's going to use. However, most of the time it's probably going to sit lower than the limit. The actual memory and CPU consumption of that particular pod is going to sit a certain degree below the limit, and this is where you basically got you're over sort of provisioned, if you like. Unless you expect that traffic, the resource consumption to go up and down in peaks and troughs, you generally wouldn't want to do this. And you'd use a burstable class for pretty much anything that, like a web service or web server or anything like anything that's sort of stateless, because you don't need to worry too much about it. If it gets replaced and spun up on a different box or on a different node or moved or whatever, it's not really a concern. That's the job of the control plane. So you typically use your burstable class for just normal stateless workloads, web servers, web services, etc. And then you've got the last class, which is called the guarantee class, is where you set the request limits of the CPU and memory to match. So the requests and the limits of CPU and memory to match each other. And this basically sort of guarantees the amount of resources that particular pod is going to get. That's good for stateful workloads like databases. So if you're running a database within your cluster, I mean, I'm not saying you should do that, but if you do in a development cluster or a test cluster, you would look to set the limits the same and allocate, so it's got a predictable amount of resources available to us, and it's not very unlikely then to be moved around as much. All right. So if you're looking for stability with a particular workload and you don't want it to be evicted and you don't want it to be moved around, use a guarantee class. If you don't really care, use a burstable class. Almost never use a best effort class. And in a production environment, there would be something to enforce policy that says, well, if you try and deploy something that doesn't have any resource configuration, then it would reject it, because we don't want those in a production environment, because they would have unexpected or unintended consequences that would be difficult to track down. And the interesting thing here at the bottom, the reclamation candidates. So I mentioned previously that from time to time, your pods may stray into above the eviction threshold, so above which the Kubernetes controller is going to go into sort of protection mode, and goes, well, actually, I don't want to risk crashing this node or running out of memory in this node or CPU, so I'm going to choose a pod. I'm going to choose something that's running on that node to evict. And what it means by evict is terminate, quite simply, and move it to somewhere else that can fit it. And if it can't fit anywhere else, then we're back in the auto-scaling territory, where we'll provision more resource to schedule that pod. And this is how we can sort of do that scenario I said before, where we can run a fake sort of deployment that consumes all of the resources on a node so that would be something with a best effort class, if you like. It wouldn't be doing anything, but it would just be sitting there consuming all those resources. Because it's got a lower priority, anything coming along that has a higher priority will replace that pod, and then it will get rescheduled on the new node when it becomes available again, just to hold it in place. And that works a lot of places. The reality of this then is, if you've got a node that's running a database, but it's also running some other containers on it with burstable classes, if at any point that node becomes under pressure and the overall resources allocated to it start to creep above the eviction threshold, there's a very small chance then your database is going to get killed and popped. The likelihood is one of your burstable class pods is going to get moved to another pod, but that doesn't matter, because you're already running many of those anyway across the fleet. So you probably wouldn't even notice that happened. It would just happen in the background. So you can do some interesting things about, not just blindly let Kubernetes sort of manage all your workloads. In more advanced scheduling, you can actually control or give hints to the control plane about where you want to run these things, how you want to guarantee the sort of levels of service they have. And all these things come together, allow you to build a really sort of robust production system that requires very little sort of manual intervention. So moving on to downscaling. So I've said previously, just to remind you guys, so basically removing cloud resources when your cluster's not in use. What this really means is that you might scale down a deployment to 0 containers, which would allow your cluster autoscaler then to pull in effectively, because the resource utilization overall is quite low. Or if you weren't, using Kubernetes, what you would do is effectively the same thing. You would schedule the termination of some of your instances, or scale your auto-scaling group in using an automated sort of schedule event based on a metric or something like that. And that's obviously going to save you money in the long run. Again, you can argue that if you're, go back to the purchase options we talked about earlier, if you're already paying for these, then you might want to leave them running, but you might decide to sort of pay for a baseline or reserve a baseline capacity and then just allow a little bit of extra on demand to meet that demand as and when you need it. And you don't bother reserving that because the time that it's running is less than the time, less than sort of, should we say, 40% of 8 hours a day. Yeah. So if that extra capacity is only required for sort of 4 or 5 hours, then there's no point actually reserving that because you'll be paying less anyway by the virtue it's only running 4 or 5 hours. As soon as that extra capacity is needed for 8 hours plus, then you probably want to reserve it because overall you'll be saving a little bit of money. But some key points here is that you obviously want to leave enough capacity for high availability. Don't scale everything down to 0 or even 1 in some cases. You always want 2 of everything. So like I say, at an EC2 level, you'd want 1 EC2 instance per availability zone. So if for whatever reason AWS had an issue in 1 availability zone, your systems are still available in another. And the same with the deployment. If you anticipate some load, just keep 2 replicas because if 1 crashes, then it'll be replaced. It's very unlikely that 2 are going to crash at the same time for whatever reason. So your applications are always available as well. And what you can do is there's a couple of tools here. So things I've done in the past with EC2 is quite literally sort of dev and test environments. They're outside of office hours. They shut down. You might be using for 8 hours a day. They're terminated. Nobody uses them till the next day. They spun up the next day. That's one way you can do it. And you can apply that sort of same practice to your pods by using a tool called a queue downscaler. So it will identify you. I haven't actually looked into the docs for this, but it'll work out. It'll probably work out. You'll annotate your pod to say, I only need it between these hours. It'll watch for those annotations and then create a schedule internally to shut it down for you or scale it down to 0. So it'll be quite simple in how it's implemented, but probably quite effective. And it saves you sort of doing it manually. And then we've got the final sort of activity, which is sort of the purchase options, which we've sort of already talked about, in various guises today. So we've already established that on-demand instances are the highest price points. If you're using them for more than 8 hours a day, if you're using them for more than 8 hours a day, then you're typically using them for sort of 24/7 workloads, then reserve them. That's good. However, if you do have some workloads that maybe are not customer facing, like background jobs, then what we can do is we can provision a separate set of a separate node group within the cluster. So we've got a main node group that runs on reserved instances or on-demand instances. We can have another node group that launches spot instances for your cluster. And you can basically hint to Kubernetes about where to run certain workloads when you deploy it to the cluster. And we've already established that those workloads can be, or those machines can be significantly cheaper, up to 90% cheaper than the on-demand prices. And we've also established that these workloads need to sort of tolerate the interruption. So at an architectural level, we need to ensure that if you kill a job halfway through, it can start again and resume from where it left off. And I'm not going to cover it today, but I'll be happy to sort of cover it as a bit of an additional thing within the POC work through, because this is very much a cluster administration type thing. So whoever set in a cluster would deal with this. You can use the advanced sort of scheduling techniques to control where sort of pods in place. And there's 2 types. There's sort of taints and tolerations, which are around nodes. So it's basically saying you can have different classifications of nodes. So these are our on-demand nodes. These are our spot nodes. These are customer A nodes. However you want to slice and dice your compute resources within your cluster, that's absolutely fine. And then you've got affinity and anti-affinity, which are tied to the pod. So you can sort of hint to where that pod should be placed. Should it be placed on a particular class of node? Can it be placed anywhere? Does it need to be placed close to another pod? So if you think about instances where you might have a web service and you use Redis as a cache, you may want to deploy. So wherever you deploy your web service to, you may want to deploy a Redis cache locally to it, because it's going to be much easier to query a local cache than it is to sort of query a cache that's sitting on on a different node within the network. So you can do really very fine-grained controlling of where you want to put these things in reality. It's just that it again depends on your sort of needs, if you like. And yeah, like I said, the two advanced topics I didn't really want to cover in too much detail today were sort of taints and tolerations and affinity and anti-affinity. And with the taints and tolerations, they become really important when you're upgrading your cluster, because ultimately the upgrade process, you need to basically mark a node or within your cluster as not schedulable. So effectively, the control plane would look at that. If it gets a request to schedule a pod somewhere, it looks at the available nodes. It will see that there's a taint on that node that says don't schedule anything on this. And then we go, okay, well, even though it's got resource, I can't schedule on it, so I'll schedule it on the other ones. And that allows us then to do things like drain that node. So something that we used to have to do manually, you would give a command to the node to drain all the pods, stop them down gracefully, transfer them onto other nodes, and then that would allow you to restart that pod, restart that node, for example, if you've performed an EC2 AMI upgrade. So you've upgraded that to the latest version of the AMI with the latest security updates, and that's how you would sort of basically works in simple terms. Whereas the anti-affinity is very much a scheduling decision about where to place them. So you would put, in the case of like a background job, you would basically tell it or use affinity to tell it to look for nodes that have a particular label attached to them. So in this case, if we added a custom label to our on spot instances called spot or node type equals spot, we would add an affinity attribute to the pods to say, when you come to scheduling this pod, place it place it on a node that has the node type spot on it. So this is we're talking about labels a lot, and I've seen a lot of labels floating around a lot of the manifest. Labels are really important in controlling and organizing all your cluster resources. They're such a simple concept, but it allows you to make sense of everything that's sort of deployed into your cluster and how it works for you. Whereas the underlying sort of platform itself is got quite arbitrary. It doesn't really care about how you use it. It's got everything you need in there to be able to use it to your, or adapt it to your sort of use case. And again, like I said, I'm happy to sort of take you through an example of how that would work in principle. Maybe I'll add another node group with some on-demand instances, and we can see how that works in real time. That's about it, guys. That's all I wanted to sort of cover today. There's a little bit about environment promotion as well, which I feel like it would be better with the proof of concept, because again, we can sort of run through, we can actually make a commit, we can make a change to the application, and I want to see that change sort of propagate all the way through the different environments within the POC, so you can see how it works as well. So I'm going to leave that for there. I'd rather not do it as a theoretical exercise. I'd actually do it as this is a proper working example of how it would run in AWS. But does anyone have any questions? I know that was probably a few more advanced concepts, but I think it's good to be aware of them anyway.
No, I think I'm good.
So I have one question. Yeah, Amit, go ahead.
Yes, so I have a question. Like there was a slide where we are just providing like in the selectors in the case of auto scaling, where we were where we were saying that target average utilization is 100 and the resource name is CPU. So can we provide our own custom labels here?
Custom
in the
labels.
matrix, it's
Yes, you can. Yeah. So it's you can. So I haven't done this in the POC, but you can integrate sort of your Prometheus metrics, or even not even Prometheus metrics. So let's say you can even integrate CloudWatch metrics. So even if you weren't using Prometheus as a sort of metric store, and you're using CloudWatch as a metric store from AWS, you can make decisions. So if your application is creating custom metrics, so for example, like I say, the example I gave was, every time a user logged on, you'd have a count metric that went up, or a gauge metric that went up and down. So when the user logged off, it went down. When the user logged on, it went up. you could
Right.
publish that metric, and you could then make a scaling decision based on that custom metric.
Okay. That answered my question.
Cool.
Thank you.
Yeah, so one more thing. Kubernetes supports only scale out or it supports scale up as well?
So scaling up, so we just remind ourselves. So scaling up is obviously means changing the EC2 instance size. So if that would be quite a big job if you were running an auto-scaling group that used size A and you wanted to have one that's size B. You could do it, but the way I would do it is you would create a completely new node group that's running size B. You would then put a taint on the old node group so nothing got scheduled on there, and then everything would go across. So there are ways you can scale up manually. I mean, these are exercises you wouldn't do very often. They would be in response to sort of big events with your cluster scaling out. One thing I didn't put in that last one. So that's at an EC2 level when we're talking about scaling up. There is a tool. I'm going to show you. So something I've not used yet. It's fairly new. So what it does. So we talked about vertical scaling at an EC2 level, right? So we're changing from one size of an instance to another size of an instance. We can do that. That's fine. The vertical pod autoscaler is something that runs in your cluster and basically suggests or measures your application and tells you what the limits on the pod should be. So if you remember, this is probably not a lot of useful information on there, but if you remember, let's go back to the slide for a second. This deployment manifest here, where you've got the additional resources, it will monitor your deployments and basically tell you what it thinks these should be based on the usage. So, I mean, most people will, or most engineering teams will do some degree of load testing, stress testing, and they will understand the profile, the memory profile, and the CPU profile of their application. That's what typically happens. But if you're migrating things into Kubernetes, maybe this is a good thing to deploy when you first spin the cluster up. It says, okay, well, let's put some real user load. We'll do a load test. We'll write some scripts, generate some realistic load, and then let's see what comes back with the vertical autoscaler comes back with its suggestions, and then you can set them, according to the suggestions. So that's an option. Yeah, it is.
Okay. So do we actually need sometimes cluster auto scaling like we are doing? We will do auto scaling of the pods, right, inside a cluster.
So there's yeah, I see what you mean. There's two. I think they run in parallel really, because if you took away Kubernetes and you were just running your applications on EC2 instances, and you've got one application running on it within one auto-scaling group, and that auto-scaling group's got 4 EC2 instances. That exercise of scaling up and scaling down, according to demand, is something you would still do, even when you. So that doesn't go away even when you layer Kubernetes on top, because fundamentally what we're doing with Kubernetes is we're densely and efficiently packing all our applications onto that one node, isolating all the network and the file and the process. So in terms of cost, utilization, we've got a very high utilization of our resources within the cloud, as opposed to having multiple auto-scaling groups, each of them running one application in each auto-scaling group, and having a lot of overhead in terms of memory, CPU, network that we're never really using, but we're paying for, month to month, even on reservation. So they coexist in parallel, and together they basically give you a very high percentage of utilization across your fleet of resources.
Okay.
Does that make sense?
Yep.
Cool.
So in terms of, if we talk about Kubernetes, then scale out will be the more preferable type of scaling, right?
Yeah, so initially your scaling out will basically maximize. You're scaling out at a Kubernetes level with the horizontal pod autoscaler, or even just a manual kube scale command. that will basically efficiently use all your existing resources within your cluster. And that's, but at a certain point, if you require more resources because the traffic's increasing, then the cluster autoscaler would kick in and provision you more resources, and then the scale out could continue on the new resources. So they accommodate different things in that, you know, the cluster autoscaler has to deal with the underlying cloud and the lags. If you remember the diagram here, there. So the cluster autoscaler has to deal with this part of it, interacting with the cloud provider. It's got a single responsibility. So again, I've used this term quite a few times in some of these sessions, that all these components have a single responsibility. They're not one big monolithic application that does a million things. You pick and choose what you need, and it does that one thing well. So the cluster autoscaler deals specifically with scaling up or provisioning new resources in the underlying cloud provider, whereas the horizontal autoscaler deals with looking at the utilization of a specific workload and making scaling decisions based on that. It has no knowledge about the underlying capacity, if you like, that the cluster autoscaler understands the underlying capacity. The horizontal pod autoscaler is effectively automating your job of either editing the deployment or running the kube control scale command to increase the replica count.
Yeah, okay.
Anything else, guys? No? Okay. Bunty, you said you're back 9th of February, right?
Yes.
Yeah, 9th of February. Can you just I'll be free all that week. So just let me
Okay.
know what's a good day for you guys.
Yeah, sure. I'll let you know in advance of 2-3 days in advance, so that we can plan a session on 9th, or maybe
Oh, I've lost you, Bunty.
I'll be available on 8th as well. I'll be sure to come from you in advance, 2-3 days in advance.
Yeah, well, like I said, I think minimum 3 hours. I think we'll need to go through everything. So I'll put it together a new agenda for this, which is very specific to the proof of concept, so we can see what we're going to do on the day. I think minimum of 3 hours. It may run on to 4 hours if we get
Sure. Or what we can do, either we can cover it in a single day, or we can segregate it to 2 days.
Yeah, that may be another way of doing it. If you want to keep to this, I mean, I'm always very conscious about, you know, doing that sort of cognitive overload as well. You know, do smaller sessions.
Sure. I'll let you know in advance.
Yeah, well, let's do the plan to do that then. Do another 2-hour sessions, and we'll cover all the infrastructure side first, and then we'll cover all the Kubernetes side in the second half, and we can do it that way.
Okay, sure.
Okay, guys, that's it from me. Obviously, I really appreciate you guys taking time out of your day to come and go through this. I hope it's been useful for you to sort of introduce you to these tools. Obviously, if you have any feedback, more than happy to on the content and things like that and the examples, give us a shout. I'm always looking at ways to improve these slides and introduce these topics in a good way. So appreciate it.
Okay, thanks. Then just put all your recordings on that Slack.
Yeah, I've got
page. Okay.
Yesterday's 2 and today's uploads. I'll get those done this morning for you, and you'll have the full set then.
Okay, sure.
All right. Okay, guys. I'll catch you in a bit. Well, obviously, Bunty, all the best. Hope everything goes well and you enjoy it.
Yeah, thanks. Okay. Bye.
I'll catch up with you probably in about 10 days or so.
Yeah, sure.
All right. All the best, mate.
Okay, thanks. Bye-bye.